Waves, right? So what is it? How do you describe it in simple terms? When I talk, I'm using my energy. My vocal cords vibrate. This vibration gets transferred to the air molecules. Okay, so when I speak, the air molecules vibrate. This vibration goes on to the next air molecule, vibrate, and it goes on to the next, to the next, to the next, and to your ear, and then you hear me. So wave is really just the travel of vibrations. Okay, now vibration, or also we call it disturbance. First, you need a source, right? What is the source? The source is my vocal cord. My vocal cord vibrate, the source vibrate, causes the neighboring molecules, the air molecules, to vibrate. So without the air, you cannot hear me. There's no sound, right? So that's why you need vibration of particles. Now, the first particle vibrate, it is disturbed. It is disturbed, it vibrates, causes the second one to vibrate. Why the second one? Why should the second one vibrate also? Because the first one is linked to the second one, right? How is it linked? Intermolecular forces. Molecules, they are linked to one another by intermolecular forces. It's kind of like a string. You can think of it like a string where I fix one end to a wall like this, and I hold it the other end. I do this up and down. Okay, now I'm disturbing this molecule here. I want you to think of the string like a chain of particles. It's like one particle connected to another particle like this, where this is like the bond between the particle. When the first particle is raised, it causes the second one to raise as well. It's like if you take a cable, you do it like a straight cable, and then you just press the middle here, then you see here, not only this particle is raised, the neighboring particle all here is also raised to a certain extent, right? So it's the same here. The molecules, because of the intermolecular forces, you push one, then all this they are raised. So when you do this up-down movement, if you only do one time, you create a pulse. A pulse is like just one off. It's like one time, gone. If you keep doing that, then you get a continuous wave, or we call it the progressive. Okay, the progressive wave, continuous. Okay, so the first, now it is very important in the wave concept that you understand that wave does not transfer any matter, but only transfer disturbance. Now, what does it mean? If I raise this, you will see like a pattern, right? You'll see a pattern, like a wave pattern on a string, like this. And let's say this is the string, and here is raised at this instant of time. And when the time passes, then you see this amplitude has gone here, right? Over time, then it has gone here. So this wave is like moving to the right. Look at this particle here. This particle, let's call it particle number 1. At this particular instant, this particle gained this amount of amplitude. It is raised, so it gains this amplitude. Who is giving this amplitude? You are giving it because you do this, right? Now, then when the wave come here, who is now getting this amplitude? This particle over here, particle number 2, is raised. What happened to particle number 1? Now it comes back to original position. Okay, now as it goes here, then again you have particle number 3 raised like this. Now if you just observe this motion, imagine what happened to the particle. 1, 2, 3, they are just going up, down. Number 2 is just up, down. 3 is just up, down. Do they change position? They don't change position, right? Same position, they're just moving up, down. But what is moving? This wave is, the amplitude is moving. Okay, the amplitude is moving. What is the amplitude? The amplitude is just energy. It is the disturbance. That's why we define wave as the travel of disturbance, because the particle does not physically travel from one place to another place. It is the disturbance that is traveling. It is the energy that is traveling. So you can short it as wave is the transfer of energy or the transfer of amplitude or disturbance. Okay, now there are many types of wave. There are waves that we can see, for example, like ripple. Okay, you drop a stone into the pond and you see this ripple, water waves. There are waves of a string, okay, slinky or a spring, a guitar string. You plug it, it vibrates. That is also a wave on the string. A jump rope, okay, or a stadium wave. Okay, there are many types of waves. These are the waves that we can see. There are also waves that we cannot see. Example, electromagnetic waves. Okay, light waves, we can see light, right? But we cannot see some of the electromagnetic waves like the radio waves, the UV, the infrared, and so on and so forth. Okay, so what is the one thing in common for all the waves? You have many types, but there's only one thing in common. All these waves, they transfer energy from one place to another. That is all these waves, what they all do. Okay. Now, next one. Here, there are a few terminology that you need to know. Okay, so you learn about amplitude, you learn about what else? Wavelength, and you learn about velocity of wave, frequency of wave, period, and also the phase. Phase and the phase difference. Okay, so in the always they will ask you to determine all this, to find all this, and especially the phase difference. In the past, you see they ask you to find the phase difference. Phase difference, okay, what is really phase? If you see this wave on this spring, this string here, phase is like referring to one single particle, one atom. Okay, so let's just take the first atom here. The first atom, this atom moves up and down. This atom moves in a cycle. We are just referring to one atom. Okay, this atom moves in a cycle, up, down, and come back to the equilibrium position. It's like simple harmonic motion. Okay, simple harmonic motion. Now, each and every one of these atoms do the same thing. They are all moving in a cycle. This cycle is 360 degrees. We separate into 4 sections. Okay, 4 parts, 90 degrees each. Okay, so 0 started at equilibrium position, raise up 90, go down. Okay, you have 270, and then come back here, 0. So all the particles, they are moving in a cycle. When I say that 2 particles have the same phase, what does it mean? The string, you create a wave on a string like this. If you focus on the peak, there's 2. This atom and this atom, that individual atom. What is this atom currently doing? It is at the maximum position and it is about to come down. This atom, same. It is at the maximum position and it is about to come down. So to say that 2 points that are in phase is, we really just look at 2 things. One is the location. Location must be the same. Okay, what phase they are in, right? Maybe 90 degrees. This is 90 degrees. Okay, so location must be the same, and not only location. Number 2 is that the movement must be the same. Both atoms, they are moving down. Okay, at the same time. So we say that these 2 atoms, these 2 points on the wave has the same phase. They are moving in the same stage. of the cycle. What is the cycle? The 360-degree up, down, that is the cycle. So what is the stage of the cycle at 90 degree? This one at 90 degree. What is the stage of this of this atom? This one here. What is the stage of this one? Okay, this one you move up, right? And then this one you move down. So maybe this is 180. This is 0. Okay, this is 180. This is 0 and it's 360. Okay, so that's in phase. Now in phase, phase can use to refer 2 points on the wave, or it can also be used to refer to 2 waves. Okay, so this is 2 point on one wave, one single wave on the same wave. Or you can also refer to 2 waves, different sources of waves. If I have one wave moving like this, and then we have another one that is moving same like this, then we say that these 2 sources of wave are in phase. If one wave is lagging behind like this, then they are not in phase. So this is lagging about 180. Okay, this is lagging 180. If I lag 360, that becomes the same phase also. Okay, so lagging 180 and lagging 90 would be like this, lagging 90. Right? So you can use it to refer to 2 points on one wave or 2 sources of waves. Right. So when you define wave, you have to mention there is no transfer of matter. There's only transfer of energy. It's like the best way you think about it is like you take the rope. If you mark a red dot here and treating that this dot is like the particle, you do like up, down, and then you observe this red dot just going up and down. So the particle is just going up and down, but the wave is moving like this. Okay, so 2 types. There are many categories of waves. One type of category, okay, one classification is that transverse. You have transverse and you have longitudinal. Okay, transverse and longitudinal. Transverse, the particle move up, down, but the wave is perpendicular. Longitudinal, the particle move left, right, and the wave direction is parallel. This is like how if you take like a long spring, like a slinky, long spring, and then you just push and pull, okay, you'll see the wave traveling on the spring. It's kind of like how the worm moves, something like that. Okay, you can imagine it. That's longitudinal because the particle is doing left, right. The wave propagation is also to the right, is parallel to it. So example of longitudinal, sound wave. What else? You have sound wave, you have seismic wave. Seismic waves like earthquake. Okay, when there's earthquake, you get many types of wave coming out. Actually, seismic wave can be transverse also. Okay, can be transverse and can be longitudinal. So you have seismic wave here and you have seismic wave here. How is longitudinal happen in the earthquake? It's like, okay, this is the surface of the earth, right? This is the surface of the earth. So you have longitudinal is like this. Here it pushes in this direction. It's kind of like this. Okay, let me do it again. This one is to the right, and then this push it to the right like this. Transverse is like this. Okay, the surface of the earth, like this. Okay, and then you have another type also. There's another type of wave from the earthquake. It's like we call it like shear. It's like it moves to the side. This one moved to this side. This one moved to this side. Top view is like this. Top view. This one is like this. They move like this. Okay, this is the surface of the. If you're looking from the top, then surface like this one is to the left, this one is to the right, like this. Okay, so there are just many types of waves from the earthquake, but we group it in transverse and longitudinal also. Okay, transverse, we have EM, electromagnetic waves. We have light waves. Okay, actually, light is also considered EM, and water waves, stadium waves. If you have ever been to concert, okay, then you see people sit in front, first row, all the way to the back row. The first line, the first row of people, if they stand up, they sit down. The second row repeat the same thing. Stand up, sit down. Third row, stand up, sit down. Everybody keep doing the same thing. Then you see this wave travel from the first row to the back. Okay, is the person from the front seat moving to the back? No, it's just standing up and down. Everybody just standing up and down like this. Then you see a wave moving. So the wave is traveling. The particle is same position. It's not moving. Okay, so no transfer of matter, only transfer of energy. Even if you see the tides from the water tides, you see the tide is coming. It's like you think that, okay, the water molecule is coming. No, the water molecule inside is actually moving up and down. Just the energy is coming. That is why when you put a ball on anything, like you put any object on the water, if there are tides, you find that this thing doesn't move. It doesn't move towards you. It's just going like up, down like this. Okay, so this is like, it proves that the wave is just, the vibration is just vertical up and down. Okay. Now, next one is, I want to go to the electromagnetic waves, and then I want to talk about also the polarization of waves. Okay, so there are many phenomena of waves. We are not going to talk about reflection because that's just what we learned already. Nothing new, just reflection of wave, refraction of waves. And then you have what else? You have the interference of waves. And you have diffraction and polarization. These are the few phenomena of waves. So today we'll talk about polarization, and for the next lesson, I will cover the diffraction and interference. Okay, because they are it takes more time for that too. So we'll just leave it in the next lesson. Now for EM wave, electromagnetic, you have the spectrum. Let me just clear this. Just clear this. Okay, now the spectrum, we start with visible. These are the only portion of the spectrum that we can see, right? Visible light. What is the wavelength? Now you need to remember the wavelength, guys. The wavelength that you need to memorize, because they will ask like UV. What is the range of the wavelength? You need to be able to give it. So visible is about 400 nanometer to about 700 nanometer. That is the range of visible light from red to violet. Okay. Now, if you see the spectrum here on the left, okay, we do like decreasing in the wavelength. Okay, left to right, decreasing in wavelength. So we have red here, the one with the biggest wavelength, and then we have violet on the other end. That is the smallest wavelength of the color. Okay, now after violet, what do we have for the next one? Just after violet. After violet is the UV, right? That's why we call it ultraviolet. We take the same violet, we call it ultraviolet. Here, and then we have X-ray, we have gamma. Okay, on the left, going down, we have infrared, and we have microwave, and then we have radio waves. Okay. Now we can detect visible light. because we can see it, right? Our eyes can detect visible light. Wait, who is entering? Okay. Now we can detect visible light. Can we detect other types of wave? Let's say, can we detect ultraviolet? Okay, let's start with infrared first. Can we detect infrared waves? Yes, your skin can actually detect infrared. You detect infrared as heat, as heat waves. Okay, so in other words, infrared is like heat radiation. Our skin can detect infrared, even though we cannot see it, right? We cannot see infrared, but our skin can detect it as heat. Okay. How about ultraviolet? Can we detect ultraviolet? You cannot see it, definitely cannot see ultraviolet, but can our skin detect it? Yes, our skin can also detect ultraviolet, but just with a bit of delay, because when you stay under the sun long enough, the next day you get sunburn. That's ultraviolet. Okay, you only know you are exposed to ultraviolet the next day. So that's delay. So your skin can also detect ultraviolet, but there is a time delay, UV. Okay, now what is the wavelength of UV? About 10 minus 7 meter to 10 minus 9 meter, even smaller than the visible spectrum. And X-ray, you're going to the right, you get 10 minus 9 meter to 10 minus 12. And anything that is less than 10 minus 12, we consider it, we just call it gamma rays or less. Okay, we did not do any category after gamma. It's just anything less, we just call it gamma. To the left here, this is about 10 minus 5 meter. What about microwave? Microwave is like about like this size, like physically this size, about a few millimeters to centimeters. Okay, so we have here a few millimeter to a few centimeters. It's like about like half an inch, something like that. That is the wavelength of microwave. Okay, that is the wavelength of microwave. And radio wave ranges from meters. Okay, we're talking about meters, something like that. Okay, meters to miles. Meters to miles. Okay, it can last very long. Anything that is higher, we just call it radio waves. Okay, you see, if I want to detect a wave, I want to pick up a signal from a wave. I want to detect a wave. The detector at least need to be as big as the wavelength of the wave that I want to detect. For example, radio waves. If I want to detect radio waves, the wavelength is about meters, right? So I need a detector, a device that need to be at least meter to pick up the radio wave. If it's shorter than the wavelength, then the wave would just like pass through like that. It would just wash through like that. Nothing happened. Sorry. Okay. So that is why if you see the old TV, the TV with the antenna, how long is the antenna? Before we use cable for the TV, we use antenna, right? So how long is the antenna? About a meter, right? About a meter. So because we want to pick up the radio waves. Same for microwave. The wavelength is millimeter to few centimeter. If you want to detect microwave, walkie-talkie. Have you seen walkie-talkie? It's like we don't use it now already, right? So it's like the people use it for short-range communication, right? When you press the button, then you can speak through it, and then you release it to listen. Okay, we don't really use that much right now. That one, if you look at the antenna, how long is the antenna of the walkie-talkie? About a few centimeters, because it transmit and receive microwaves. Okay, so the detector need to be at least as big as the wavelength. Now, the same thing here. If you want to block a wave, let's say I want to block a wave. I don't want it to penetrate through this this thing. I need the spacing and the holes. If you look at your microwave oven, if you have a microwave oven, you look at the microwave oven, the lid, there is one layer of glass, there's one layer of plastic, and there's one layer of metal plate, like with holes on it. It's kind of like one piece of metal and then you have holes on it. The microwave oven, right? They send microwave, okay, but microwave, right? They can easily pass through glass and plastic. They can pass through the glass and the plastic. You see the lid, the glass and plastic do nothing one. They will not block the microwave. Okay, they do not block the microwave. It is the metal plate with holes that is the one that block the microwave. Okay, so to prevent any leakage, make sure that that one is sealed. It's like it's closed, not the plastic. The plastic is just for you to see. The glass is just for you to see inside. Okay, so this metal plate is the one that blocked the microwave. How does it block the microwave? You see, the microwave wavelength is millimeters, right? Millimeters. And you see the holes. The holes is no smaller than millimeters. It's like it must be bigger. Oh, sorry. Let me put it again. The holes cannot be bigger than the wavelength of the microwave. All these holes must be smaller than the wavelength. Cannot be bigger. Okay, that's why you see the holes are very tiny. It's very tiny. If the hole is like a 5 cm, then the microwave can pass through. Then there's a leakage. Okay, so to block a wave, you have to make sure that the holes cannot be larger than the wavelength of the wave. The same for all waves, not just microwave. The same for all waves. Why don't we just use like a piece of metal without the holes like this? You can use this. Okay, if you use this, you are able to block the microwave also. But just that they feel like it's a waste, right? Because you can actually cut out holes on it. You can reduce the weight of it. You can reduce the cost. You reduce the material, and still you are able to block the wave as long as the hole is less than the wavelength. Okay, now radio telescope. Have you seen a radio telescope, like the big dish? You just go and search radio telescope, you see this big dish, and then with holes on it. It looks like a mesh, like a wire mesh. Okay, it looks like a big dish, and then it has something like this. Then you have like holes on it like this. Again, this one receives radio waves. This dish needs to reflect the radio waves to the signal, the detector. Okay, here it needs to reflect. When the wave hits the dish, then it is reflected to the signal here. This receiver, okay, receiver here. So this one, they make holes on it is because you can see the holes is no greater than the wavelength of radio waves. It cannot be greater than meters. Okay, so why do you want to make this? Again, save cost, so that it's lighter, so that the rain can go through, and at the same time, they can block, they can reflect, they can still do the job, they can still reflect the radio waves. Okay, now the same thing. Now, that also explains why the reason why gamma ray can penetrate through many objects. You see, gamma ray, what is the wavelength of gamma ray? It's very small. X-ray, gamma ray. These are what we call the ionizing, right? Ionizing radiation. What's the difference from the rest here on the left side of the spectrum? Ionizing is like the dangerous one because they have enough energy to excite the electron of the atom. Okay, they have enough energy to remove one electron from the atom of the cell. Okay, to prevent this, this can cause like a mutation. This can damage your DNA molecules. So on the left, still they have energy, but not as high as the X-ray and the gamma ray. Even UV, if long exposure, you get cancer. Okay, so these are we call the ionizing radiation because they are able to ionize the electron from the atom. So gamma ray, what is the wavelength? 10 to the minus 12 meter or less. It's very, very small wavelength. If the wavelength is so small, how do you block gamma ray? You need something that is smaller than the wavelength to block it, correct? Just like our microwave here. The hose is smaller than the microwave wavelength. The radio telescope is smaller than the wavelength of the radio wave. So if you want to block the gamma ray, then you need something smaller than the wavelength of the gamma ray. How can you find it? You see, how small is it? 10 power minus 12. Do you have something that is like 10 minus 12? Even the spacing between the molecules, still bigger than this. The spacing between atoms, molecules, okay, is still bigger than this wavelength. So gamma ray can pass through. That is why gamma ray can pass through many material, many objects. Okay, they can pass through concrete, but if you make a concrete very thick, then they cannot pass through. I mean, you can reduce the percent, the how much gamma ray can pass. Okay, so that is why if you want to block gamma rays, like you have seen in the radioactive plant, people they wear the protective gear. Okay, they wear protective gear. They cover with lead. Lead. Why lead? Lead is very dense material. What does it mean when it is very dense? That means you take the substance. If you just take 1 cm or just 1 cm cube, you find that there are many particles inside, packed. It's very packed. That is dense. If it's very packed, that means the spacing is very small. The spacing between the molecules. Okay, so it's like you have this 6 molecules. The spacing is large between one atom and another atom. If you have the same volume, but you have 1 million, like 1 million atom inside. So this is very dense. This is less dense. This 1 million is become very packed, and the spacing becomes smaller and smaller and smaller and smaller, that they can almost block the gamma ray. Okay, that is why they use lead to block the gamma ray, and not entirely. You cannot block like gamma ray 100%. Still there are, you take the lead, gamma ray come here, still there are about 10%. If you have 100% coming, 90% is blocked, and still 10% can pass through. Okay, and sometimes they use lead, or you can use concrete. Okay, you can use concrete, but the concrete has to be very thick. In the nuclear power plant, they use the concrete as the shield. Okay, inside the nuclear reactor, the nuclear reactor is placed inside this concrete shield, this housing. How thick is the concrete? A few feet. It can up to 5 feet. Okay, 5 feet concrete. It's very thick concrete. Okay, 5 feet concrete. Then that can reduce the penetration of the gamma ray. Okay, so in this spectrum, now when I say light, it can mean radio wave, microwave, infrared, not just visible light. Light is a general term for all the EM waves. Visible light is just a portion of it. What's difference in this spectrum is only the wavelength. or the frequency. Across the spectrum, the wavelength decreases and the frequency increases, and the speed is the same. So it's like, that's why we say that the spectrum is continuous. Okay, it's all connected. The only difference is that the different frequency that they are vibrating. Okay, it's all connected. The smallest wavelength, you see, when we see stuff, right, we see objects around us because of reflection of light, right? So we see stuff around us is because light falls on the object, reflected off of it into our retina. That's how we see the object. So it's because of reflection that we see things around us. Look at the visible light spectrum. Violet has the smallest wavelength, right? Violet has the smallest wavelength and red has the largest wavelength. Beyond violet is ultraviolet, which we cannot see. So the smallest that you can see is the violet. In other words, I say that the smallest object that we can see is the wavelength of the violet. Okay, again, the smallest object that we can see is object that is as small as the wavelength of the violet. Okay, because violet is the end of the spectrum. This is the last color that you can see. So the wavelength of the violet, any object that has the same wavelength as the violet can reflect the violet. Any object that is smaller than the wavelength of violet, it cannot reflect. That's why we cannot see. Okay, we cannot see. So the smallest that we can see is the object as small as the wavelength of violet. That is why you have the optical microscope. There's a limit to the optical microscope because there's a limit to the wavelength of the color violet. If I want to see smaller, what do I do? If I want to see even smaller, I will use a wavelength that is smaller than the violet. So ultraviolet, but the problem is we cannot see ultraviolet, right? You can use ultraviolet, but we cannot see it. Even though it reflects, you still cannot see it, right? So what do? They found that electron, but the thing is, electron, does it have a wavelength? Electron is just a particle, right? But the thing is that electron is also a wave. It's also a wave, right? This one will cover more in the coming chapters when we go to the quantum physics. Okay, when you go to quantum physics, you'll study about the particle and the wave. They are actually the same thing. Okay, stuff. Right. So electron, they found out that electron is also a wave, and it has a wavelength. Electron has a wavelength. That sounds weird. So the wavelength of electron is almost the same as X-ray. This one. Okay, the wavelength of electron is almost the same as X-ray. Then, because electron has a wavelength, so they think that, okay, we can use electron to see even smaller objects using the wavelength of electrons. That is how they get the electron microscope. Okay, electron microscope. Optical microscope, you need light, right? Usually we have it in our lab. Electron microscope allows you to see even smaller objects, even more detailed, very detailed. The images, if you take images from Google, like the red blood cell image or the bacteria image, those images that are very clear one, very detailed, very clear one, those are usually taken by electron microscope. Okay, because optical microscope you cannot do that. Okay, those are actually taken by the most the tiniest detail that you can see is all taken by electron microscope because the wavelength is much, much smaller than the violet, the visible light spectrum. Okay, now what you need to know in this part is that the wavelength, of course, you need to remember the wavelength, and what else? The function of each wave. Okay, the function of each wave. UV, okay, radio wave communication, microwave cooking, okay, the application of it, okay, the application of it, and infrared, like remote control, all that, heat waves, radiations, visible light, of course, allow us to see. What about UV? UV ray, what is it used for? You may have seen in the movies, the crime scene. What they do, they close the light, and then they shine this black light, and then they can see like all this stain glowing in the dark, like blood stain. What else? Like even body fluids, urine. Okay, all this body fluid, blood, urine, you can see it. All this stain is missing inside. You cannot see it with visible light. They have to close the light, and then they have to shine this UV. This, we call it the black light. Then you can see all this stain to get evidence. Okay, so what is this black light? You have heard, like, you have seen also highlighter that can glow, like highlighter can glow, and you have seen neon light. Okay, all this are made of, it's kind of related to black light, because black light, why do we call it black light? Black light is actually UV light. Sometimes they mix the UV with a bit of violet, okay, just to reduce the exposure to UV. Because if they make it pure UV, then it can be like dangerous to people also. So sometimes they mix it with violet. So that is why sometimes you see it's like purple. This light is purple light. And the counterfeit money, the device used to detect the fake money, you press, you see purple light, right? So that is also black light. It's UV plus violet. Okay, so black light, why do we call it black? Is because you cannot see it, in the sense that when you switch off the light in the room, it's all dark, and then you open this black light, you still cannot see anything. You cannot see it because you cannot see UV light. Okay, but how, if you cannot see black light, then how do you see the stain, like on the floor, on the bed, anything? How do you see all these blood stains? Is because blood, usually it contains what we call the phosphor. Okay, phosphor, it's something that if you shine the UV on it, this phosphor will absorb the energy, because UV has enough energy. Towards the right region of the spectrum, they have higher energy, right? So this have enough energy that if you shine on the blood, the content of the blood, the phosphor, it absorbs this UV, and then it can emit another wave of different wavelength. In other words, they emit light of different wavelength, wavelength. Okay, so that means they glow lah. They glow. You shine the UV, they glow. Get the blood glow, the urine glow, all this. So that's how they detect all these evidences. It's because it's like the fluorescence effect. The fluorescence effect, like the one in the CRO, the one in the lamp, fluorescent lamp. Okay, all this is because of the phosphor. It absorbs the UV, absorb the wavelength, and then emit again. But this time they emit another wavelength. Okay, so these are a few applications of the EM waves, the UV, X-ray, and the gamma rays. You can just read up from your notes or text. Okay, we are going to have a short break and we'll come back again at 8:03. Okay, we'll come back at 8:03. We'll continue the next one. Okay, we are back. Okay, polarization of light. There was a experiment conducted in the early days where they put a chair in front of them. It's like they put the chair here, and then they take a tourmaline crystal, a piece of tourmaline crystal. They hold it here. They point this crystal facing the chair, and then they look through it. Okay, they look at the chair through the tourmaline crystal. Let's call this number one, crystal number one. And then they put another one. They take another crystal, same crystal. They put it at the back of the first one. Okay, in front of the first one, And then they see from here. This is number two. When they rotate this crystal, right, at first they can see the chair. Okay, the first one, after they put the first one, they can still see the chair, but just a bit dimmer. Okay, a bit dimmer. And when they put the second one, they still can see the chair. Again, it's a bit dimmer. As they rotate the second one, they then rotate this second one. Rotate until it becomes 90 degrees with the crystal number one. Okay, so it's like they make a cross like this. Become 90 degrees, and suddenly they see the chair disappear. They are not able to see the chair. Okay, they are not able to see the chair. Again, like this, they still can see the chair. When they rotate, then they found that it becomes dimmer and dimmer. And when it's 90 degrees, then they cannot see through the crystal anymore. So what is happening here? They were unable to explain. Later that they found out there's one more property of light. We have reflection, refraction, interference, diffraction, and we have one more property of light that we call the polarization. Okay, let's understand what is really polarization. Now, the molecules of the okay, let me start off by just talk about like what light, how is light generated, what light really is. The EM wave, right? How is light generated? You know that it is electromagnetic wave, right? EM wave, but it is generated by the oscillation of electron. Again, just now I said that the rope, when you oscillate the atom, what you generate? You generate a wave on the spring, on the string, right? On the rope. This is the oscillation of atom. Oscillation of atom, you generate this wave. Now, when you oscillate electron, let's say you oscillate electron, because electron has a charge, it has an electric field. You oscillate electron, then it creates this electric field that push through space. Push through the space, they push forward, you get this electric field, the wave. And also there's electric field, and there's magnetic field. That's how you get this. It's kind of like this perpendicular wave like this. If you see from your the notes given by your teacher or your textbook, you see the electromagnetic wave. It consists of electric and also magnetic. Okay, how is that generated? It's from the oscillation of electrons. So this wave does not, like, physically, you cannot touch it, right? It's not, unlike the rope, you can touch it. It's actually, you can touch this all this, but this one you cannot. And they travel through vacuum. They travel through vacuum. So as these reach the earth, this one, okay, reach the earth, when we pick up this signal, right, this electron, they vibrate in all different directions, not just up, down. They vibrate left, right also. they vibrate diagonally also, like this. So we are going to represent the vibration of electron like this. Here we have up-down vibration. This is front view. It's like the light is coming towards us. We are looking directly at it. Okay, so this is the vibration of the electric field. And also you have a vibration in this direction. Also you have vibration in this direction. In reality, they are just like everywhere, 360 degree everywhere. Millions of vibrations. It's like a mess. But here, just to simplify the everything, we are just going to take cross and then diagonal. Okay, but in reality, there are many vibrations everywhere. Okay, so this is the vibration of the electric field. This is coming from the sun, reaching the earth. This type of light, we call it unpolarized. Okay, unpolarized. That means the electric field is vibrating in all directions, unpolarized. This is front view, right? Now, if I want to sketch the side view, I would do something like this. I will write an arrow showing the propagation of the light. And then I will do a dot. And then I'll drag the arrow like this. Okay, the dot is like looking from the side. The dot is vibrating to and fro, like towards you and away from you. Imagine that this dot is like this dot is actually this one. This one. Let me point it here. This dot is this dot is actually this one here. Imagine like we are looking from the side, right? So you see the up down, which is this one. Okay, this one is this one. And then you see this one, which is the dot, represented as the dot. So it's like kind of, you can imagine that this field is vibrating towards your face and away from your face, towards your face and away from your face. It's like out of the screen and into the screen. Okay, so that's how we draw the unpolarized light. That's how we represent it. Okay, in the 2D view, like this. Okay, at the side view. So we draw like this, and then we have another one. We have another one. Okay, so it's like we're seeing from here. The light is reaching us like this. This is also unpolarized. Again, what is unpolarized is light where the electric field vibrate in all directions. That is unpolarized. Okay, so what is happening in that experiment, the chair experiment? You see, the tourmaline crystal, the spacing between the molecules, they form a unidirectional windows. What does that mean? This is the molecules, they line up perfectly, that they form this vertical opening. Okay, this vertical windows. That when there's a light coming, okay, now the unpolarized light coming, the vibration is in all different directions, right? So what happened when the horizontal vibration pass through the tourmaline crystal? Can it pass through? It cannot pass through because the opening is vertical like this. Okay, so the horizontal come here and it is blocked. The diagonal come here, it is blocked. Like this also, it is blocked. Only the vertical vibration can pass through. Only the vertical one is allowed to pass through the tourmaline crystal. Okay, so you can think of it like the molecules are arranged in such a way that the opening is vertical like this. Okay, now to represent it in a diagram, we just draw like this. We draw like a piece of crystal and then we do like this. This means that the windows is vertical. Okay, the windows is vertical, the opening is vertical. This thing, the crystal, sometimes they call it the polarizer. The polarizer. What is a polarizer? Something that allow or block the light coming through. Okay, so if it's a vertical, then it only allow the vertical come through. So what happened here? Now, at first, you have unpolarized light from the chair coming to the first polarizer. When it passed through, only the vertical is allowed. So after this, only this. Like this. I draw a diagram like this. Okay, the horizontal one is already missing. After the first polarizer, what happened to the intensity? You see, I already removed the horizontal one, left only the vertical. So half of it is removed. That means 50% is reduced. This is 100%, that's 50%. It becomes dimmer. Can you still see the chair? Yes, you can. As long as there's one light that can go through, you can still see the chair. What does it mean? Like if you have 100 rays, right? If you only see one ray, you can still see the chair. You can still see the picture. It's just that it's going to be very dim. Okay, so at least as long as there's one light, it's able to form a picture. So you still see the chair. Now, what happens when it passes through the second one? Now, just now I mentioned that they rotate, right? They rotate the second one. As they rotate, this thing, when they rotate 90 degrees, then this one become what? This one become horizontal. Now it become horizontal. The second polarizer become horizontal, but you have this vertical coming in, and all this vertical also it is blocked. It cannot pass through. So as a result, what is coming out from the other side? There's nothing coming out from the other side. So what do you see? You see black. There's no light coming out. You can search this. You can even see they have a lot of videos on these things, right? This thing, when you rotate this, suddenly you see black color. You cannot see through it anymore because there's no light can come through the crystal. Okay, so this is we call the first one we call the polarizer. Usually we call it the polarizer. And the second one we usually we call it the analyzer. Okay, let me explain why do we call it analyzer. This one we call it the analyzer. Because we use the second one to tell whether the light is polarized or not. How do you know whether the light is polarized or not? You take the analyzer. When you rotate the analyzer, if you do not see the chair, then you know that the light coming before the analyzer is a polarized light. Because if the light coming before the analyzer, okay, is unpolarized, you rotate it, you still see the chair. You rotate, you still see the chair because there's horizontal can pass through. Okay, so that is why we call it the analyzer, because it allows us to determine whether the light that is coming to us, is it polarized or is it unpolarized? We do it by rotating. I do not see it, it's polarized. I still see it after I rotate, then that is unpolarized light. Okay, understand? Now, the middle one, after they pass through the first polarizer, this one, the middle one, is we call it plane polarized. Plane polarized. Why plane polarized? Because it's just one plane. Vibration is just in one direction, vertical. So one plane. That's why we call it plane polarized. After pass through the first polarizer, it becomes plane polarized. Okay, and the second analyzer, depending on whether you rotate it or not. Now, when you rotate, right, the intensity will also decrease. Okay, so it's like this. You have the first polarizer vertical, the second polarizer also vertical, but this one you can rotate with an angle like this. Sorry about my drawing. Let me make it better. Okay, so you have this, and then like this. So this one you can rotate. You find that when you rotate, as you rotate more and more, right, the intensity decrease more and more. And when you reach 90 degrees, then no more light. So as the angle increases, the intensity will decrease. Okay, that's one takeaway from here. Right. Okay, now the polarization of light can be achieved by many ways actually. One way is you can use a polarizer like this one. You can make it polarized. Another way is by reflection. Even normal reflection, still the light can be polarized. Like the ground. Say you have the ground here, and then when you have light coming from the sun, so you have unpolarized light. Here I'm going to draw like this. Okay, so this is unpolarized light coming. When it hit the ground, right, the vertical one will be absorbed by the ground. And the reflected one would be the horizontal. Okay, it's like same as the surface of the ground. Just imagine that the vertical will be absorbed inside, because the horizontal one is kind of like parallel to the ground surface, right? So when it hits, it bounce off, only the horizontal one will be reflected. Okay, because reflection is never 100%. When you have 100% of light hitting an object, after reflected, it's going to reduce to maybe 80, maybe 50, maybe 60. So some part of it is being absorbed. Okay, so reflection after absorbed, you get also polarized, but this is only partially polarized. What does that mean, partially polarized? Partially plane polarized. If you compare to the polarizer, this one is like mostly all of it is vertical. Mostly all of it is the same plane. But this one, if you see this one, you see some are horizontal and some are vertical. It's like never perfect. That's why we call it a partially polarized. Reflection is partially polarized. Okay, partially plane polarized. But not as good as the analyzer. The analyzer can make it all plane polarized, but the reflection is just partial. So meaning that you will find some horizontal, mostly horizontal, yes, but sometimes you'll find like a vertical or a diagonal, something like that. Okay, different directions. Okay, so that is the second one. Polarized can be achieved by, first is by filtering. That is the polarizer. This is filtering. Second, by reflection. This is reflection. Third is by refraction. Okay, refraction also will polarize. Like, for example, the light goes from air into water. There's a refraction. Again, you have unpolarized light coming here. After it go to the second medium, water, then it becomes polarized, partially polarized also, partially polarized. But seldom they will ask that, just to give you a general idea of different ways that you can polarize a light. Okay, now, why is polarization important, and what is the application of polarization? You have seen Polaroid sunglasses, and you have seen 3D goggles, 3D movies, all based on the principle of polarization. And also the main purpose of polarization is to cut glare. What is a glare? See, let me erase this. Okay, first is to, let me put it like this, cut glare. Okay, now, what is a glare? So you may have noticed that sometimes during the night, when you see like a cyclist with the lamp, with the headlamp, and suddenly nearby got a car pass by, and the car headlamp is very bright. Okay, it passed by, then suddenly you cannot see the cyclist anymore, right? Because the lamp of the car is too bright that you cannot see what is surrounding, what is at its surrounding. Okay, so that we call it the glare of the headlamp of the car. So what is happening here? Why you cannot see the surrounding? Because there's something that is so intense, right? There's something that is so bright that it captures your attention, captures your eye retina attention, so that you cannot see what is surrounding of the object. So let me explain. You see, this is your pupil, okay, and it can adjust itself. Sometimes it dilate, right? When you go to the dark room, it dilate, expand, and when you go to bright room, then it becomes smaller. And at the back is your retina. Let's say this is the cyclist, okay, cyclist, and then there's light coming. It's light coming. Now, here, if the cyclist, the light it has a low intensity, it's not bright enough, then you need more light. You need more light to fall on the retina just to form a picture of the cyclist. Okay, so when you need more light, because the brightness is not enough, when you need more light, the pupil will expand. Okay, it will become bigger. That is why when you go to a dark room, it becomes bigger, because there's low light, not enough light, not enough intensity. So it becomes bigger just to capture more light. Okay, so you have this, it expands, it gets more light, and then more light falls on the retina. So let's say it's 100 ray. And then it is able to form a picture of the cyclist. Okay, now, suddenly the car comes. The car, which has, the headlamp has a brighter intensity, has a higher intensity. So suddenly you have a lot of light ray coming in. And the total amount of ray fall on the retina become 200. This is 100%, this is 200%, double. Your retina cannot bear it, cannot bear it. So what happened? If like this, then it will be damaged. So what happens is that it communicates with the pupil, then it will start to decrease in size. So the pupil becomes smaller, like this, so that this one become, again, drop to 100%. Okay, now, once it becomes smaller, what happened to the light coming from the cyclist? Initially, it is this big, capturing all the light from the cyclist. Now, after it has reduced its size to this one, smaller, then that means the amount of light ray coming from the cyclist reduce. Initially, how much? 100 coming. Okay, initially 100 coming. Maybe now you're only receiving 25% from the cyclist. The remaining 75 is from the car. So that means the main focus has shifted to the car, because it has higher intensity. So if you are receiving low light 2025, then it makes it very difficult for you to see what is the cyclist. Okay, because you have something that is so intense and something that is less intense placed side by side. Okay, you can hardly notice this one. That is we call glare. Okay, glare. So the polarization used to cut glare. How does it use to cut glare? In the headlamp of the car, we use a polarizer. Okay, we put a polarizer in the headlamp. When the light come out, it goes through this polarizer and the intensity is reduced. Okay, so it's reduced 50% because from unpolarized, become polarized. If you want to polarize it, the intensity will reduce. Okay, so reduce minus 50%. So this reduces the glare in the night. So that's the first one, okay, to cut glare. And also the same concept for sunglasses. Sometimes when you see reflection on the mirror or reflection on the water, the reflection from the mirror is so intense that you can hardly see the mirror itself. You only see the reflection. Okay, it's kind of like a bright spot, very bright, like just from coming at you, right? So when you put on the sunglasses, what happens? It feels more comfortable. Okay, it feels more comfortable. It's not that intense, and you can see very clearly. It's kind of like adjust the contrast around you, the vision. Okay, so what is happening? The sunglasses, not all sunglasses are the Polaroid sunglasses. Okay, the sunglasses, they use the lens of the sunglasses. They use a filter. Again, like this. Okay, so remember I said that earlier. I said the light is polarized after reflection off the ground. Okay, so when you have light coming here, unpolarized light coming here, and reflect off the ground, it becomes partially plane polarized, like this. And it's horizontal, right? Horizontal. So if you're driving, you put on the sunglasses, and your sunglasses is like this. Vertical pass. This one we call it vertical pass because you only allow the vertical to pass through. With the lens that has a vertical pass, then this one cannot pass through. So that means you cannot see the reflection of the ground. Okay, not entirely because this one is partially, right? Partially plane polarized. You kind of reduce the amount of light coming off of the reflection. Okay, so this reduce the glare, the reflection on the ground, reduce the bright spot. Same for glasses, windows, water. The same use in photography. Okay, the camera in front, they attach another filter, the Polaroid. Okay, filter. And they take better images. They make the sky become bluer, they make the water become clearer. Because sometimes when you take a photo of the water, right, you only see the reflection. You cannot see the water also. You only see the reflection. It's like very bright, very white. Okay, but if you reduce down the glare, then you can see the water bluer, okay, clearer. You can see it. That is all the application of polarizer. And number 3, the last one, 3D glasses. Same thing. Polarization. How does it work? Now the 3D thing is very long process now. It's very long technique. But just to long story short, just to cut it short, how do we see 3D? By the way, you need 2 eyes. Because let's say, okay, you're seeing the face of a person. One eye can see here, this one until here. This eye can see the left ear, but cannot see the right ear here. And another eye can see the right ear, but cannot see the left ear. Okay, both eyes receive light ray from different perspective. Your brain then, based on all this information, they form a sculpture, like a 3D sculpture of the object, and allows you to see in 3D. Okay, so again, this one is images coming from different perspective. Based on that images, your brain forms a sculpture, a 3D model of what you are seeing. One eye cannot see the depth. If you close one eye and you ask somebody to pass you a ball, you'll find it very difficult to catch it. Okay, so you close one eye, you ask somebody to throw a basketball to you. It's very difficult because you cannot see it coming. And even if you can see it coming, it's coming very fast. Okay, so if you use two eyes, then it's much easier for you to catch it. What is happening here is because you need two eyes to see the depth of an object. One eye, if I put one object here and another object behind, you're only seeing like this in a straight line. You cannot see what is the thickness behind or the depth. Okay, if two eyes, then you're receiving another ray here. This forms an angle. You're receiving another ray here. You form an angle, and based on this, your brain can interpret which one is nearer. What is the depth? Is it coming forward? Is it moving backwards? Using these two images. Okay, so the point is you need two pictures to form, to form like a 3D image of something, or to see the depth of something. Okay, two pictures, two eyes. Now, in the 3D cinema, what they do is they project two images on the screen. Okay, there's a problem with the screen because the screen is 2D. Okay, if the screen is 2D, then the light coming out is 2D. Then you cannot see in 3D. There's only one image. There's only one image. Unlike in real life, okay, where you have different perspective, right? In real life, you have different perspective. You stand here, you get an image here. You stand on the left side, you get another image here. But on the cinema screen, there's just one screen, one picture. So what they do is they project two pictures. Okay, they project two pictures on a screen. That is why sometimes if you do not wear the glasses, you see like the nose is like this, and then you see another one next to it like this, right? Like two pictures. Okay, so they form two pictures, and then the whole idea of 2D is because of the glasses. So you have a glasses like this. These glasses is vertically passed, and another glasses is horizontal. And you got two pictures, right? One picture, they project it with vertical polarized ray. Okay, the cinema coming out from the camera, they project with vertical polarized light. The second one, the second camera, the second image, they project it with horizontal polarized light. Both are polarized. Okay, one is vertical, one is horizontal. And then your glasses is one vertical, one horizontal, because you want to see one picture. Okay, you want to see the picture that is only meant for that eye, meaning that this eye, you cannot see the other picture. Okay, you cannot. One eye see one image, the other eye cannot see the image meant to be seen by the first eye. That makes sense. Okay, so that's why you have this here. So let's say your left eye only seeing this image, your right eye only seeing this image. Just like in real life, left eye, you see this image. Right eye, you see this image. And then your brain do the thing, form a sculpture, and then you see 3D. Okay, again is because of polarization. Right, so that is the application of polarization. What time is it? 8:40. Okay, so we'll look at the last one small part and we will finish. Huh? Just a little bit more still on polarization is that, let me erase this first. Okay, we look at because this is also in the syllabus, the Malus law. Okay, now let's recap a bit from just now. We have unpolarized light. Pass through the first polarizer. And become plane polarized. And then you have a second polarizer here. Let's just say that we take the polarized one, this one, as the initial light ray. So we'll call this I naught. Okay, it has a certain intensity, right? We know that the first one, this one is like 100%, and this one is 50%, right? So let's just start with the second one. So we'll call this I naught, having a certain intensity. After passing through the second Polaroid, you have I, that is the I that we receive, the intensity that we are seeing. Okay, now the second Polaroid, the analyzer can rotate, right? Depends on the angle that you rotate. You rotate 90, you do not see any image. It become black. No light can pass through. You rotate, as you rotate, it reduces in brightness. Okay, so to find the intensity after the analyzer, let me write it here, intensity after analyzer. Let's say we have, okay, first we have the ray. This is the polarized ray that is coming to the analyzer. Okay, let's say that it has an amplitude of A0, like this. Okay, now I put the analyzer like this, the vertical analyzer, so it can pass through. What happens when I rotate it? If I rotate it like this. Just line up at the bottom here. I rotate it like this. And which portion of the light can pass through? Let's just say I rotate a certain angle. Okay, so only the bottom portion of the light can pass through. Which portion? This one over here. Okay, the top part cannot pass through. So I would write this like this. Only this region pass through. So the top part here is missing. Okay, now let's call this amplitude A. That is the one that passed through the analyzer, right? So we use a different symbol, A. What is this length here? This length is same as the length of the anode. So this is anode. Okay. The angle here is the same as this angle here. Okay, let's do simple derivation from cos theta. What do we get? Cos adjacent over hypotenuse. So adjacent is A over A naught. Okay, then we move like this. A equals to A naught cos Square both sides, we get a square equals to a naught square cos square theta. Okay, we are deriving an equation to find the intensity. Now, we know that intensity is directly proportional to the amplitude square. Okay, so that means here, whatever is the intensity here, intensity I naught is proportional to the amplitude square. So we can change this one to I. We can also change this to I naught. So cos square theta, the rest is the same. We get this equation here. And we can also write I is proportional to cos square theta. What does this tell us? You see this formula again. What is this I? This I is the I coming out from the analyzer. Is the I that I see, the intensity that I see. Okay. This I naught is the intensity of the light before it passed through the analyzer. Before. So you can see cos square theta, right? So that means this intensity that is coming out, the final intensity, is a portion of the initial. You have this cos square. A portion, when you put in the angle, then you see this, you can calculate the intensity. So it's a portion of the I naught. What happens when the angle is 90? What is this angle? This angle is the rotation of the analyzer. You start with vertical, 0. If you rotate it 90, like this, 90 degree, then you put in the equation cos square 90, 0. I equals to 0. No more intensity, so you cannot see anything. So when you rotate this analyzer horizontal, intensity becomes 0. Okay? What is this? This is, we call the Malu's law. Okay, it talks about the intensity of the polarized light. And sometimes the question they will ask something like this. Okay, what angle will give 50% intensity? Okay, what angle do I rotate that will give me 50% reduced intensity? Okay, then you calculate, you put in the formula. So we have I equals to I naught cos square theta, right? So then this one we put in at I naught divided by 2. We want the half of this equals to I naught cos square theta. Okay, cut. So we have cos squared theta equals 1 over 2. Cos theta equals 1 over square root 2. And you can find the angle, and you find that this angle is 45 degrees. That means when you rotate 45, that is where the intensity become half. Okay, so take note on this.